In this video, we're going to talk about sequences and summation. In mathematics, a sequence is an ordered list of numbers, and each number in a sequence is called a term or an element, and if I add those terms together, it's what we call a series. So there are two different types of sequences or series. There's finite, which is pretty obvious, it ends, and there's infinite sequences, which go on forever, have something called an nth term. So the terms of a sequence are written in a certain way where you would have what we call a subscript. So something here is I would have a subscript 1, which means the first term in the sequence. So a subscript 2 is the second term, and so on. So when you list out a sequence, you start with a subscript 1, a subscript 2, etc., which leads up to a subscript n, whether it's a finite number in the sequence or if it goes on forever and it's literally just the nth term, which is something that we don't know. Something else to know, the domain of a sequence consists of counting numbers 1, 2, 3, 4. So the domain of a sequence is the set of positive integers, and the range consists of the terms in the sequence. So something else to note is that a sequence typically has a pattern, and you can define that algebraically with a function, equation, but sometimes it doesn't. But what we're going to look at today is we're going to look at sequences and series that do have a pattern. Sometimes we're asked to write the first 5 terms or find the 4th term or something like that in a sequence. So it's really self-explanatory. So if I want to find the first 5 terms, I'm going to start with the first one, which means that I plug in 1 to wherever I see n. So that would mean it's 1 minus 1 all over 1, and that gives me 0. And I'm going to do that for the first 5. So if I expand that out and I do the same pattern, I'm going to find the first 5 terms to be 0, 1/2, 2/3, 3/4, 4/5. Something that's a bit trickier is determining the sequence from a pattern, which means that we have to work backwards. So when we're given the equation, it's easy to just plug in numbers. But if you have to work backwards, you have to know a little bit about numbers and patterns. So think of it like a puzzle. So I have 2 examples here. My first thought in this first one is, all right, I start with 1, 4, 9, 16, 25. To me, that stands out as the list of squares starting with 1. 1 squared, 2 squared, etc. So I would define that as a base n equals n squared, so that if I had a to the first, 1 squared is 1, a subscript 2, 2 squared is 4, etc. 3 squared is 9. So that pattern works for these terms that I was given here. Now, such a nice pattern doesn't really work here. I can't square it, but it's increasing by 2 each time. I've got odd numbers. So something that helps me out is I like to make a chart of the terms and then the value of that term. So let me show you. So what I have is n, so that is the number term in the sequence, and then a base n is what we actually get as far as the list goes. So the first term is 1, the second term is 3, the third term is 5, and the fourth term is 7. So as I look at that, I want to manipulate this number here to turn it into that. So I'm going to take what I first thought about adding 2 each time and think, all right, if I added 2 to 1, obviously that's not going to work. But what if I multiplied it by 2 and then take away 1? That gives me 1. Let's try it here. So 2 times 2 equals 4, take away 1 is 3. 3 times 2 equals 6, take away 1 equals 5. I should stop saying take away because it's subtract. I'm not in 3rd grade. 4 times 2 is 8, subtract 1, that gives me 7. So what I'm really doing is I'm multiplying by 2 and then I'm subtracting 1. And if I want to write that algebraically, I would express it like this. 2 times n, so whatever term that is, and then take away or subtract 1. Before we move on to the next thing, I want to make sure that I mention factorials. So these show up in series and sequences often. And remember that that is expressed by this exclamation point, and also 0 factorial is 1, and 1 factorial is also 1. And the best way to jog your memory is probably with this example. So 3 factorial just means 3 times 2 times 1 equals 6. And a very quick example on how this is really useful, and maybe you've seen this before, maybe this is new to you, but a cool little thing to do here is, so if I have 9 factorial, that means 9 times 8 times 7 times 6, blah, 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 all over 6 times 5 times 4. Now, this is going to continue with this pattern, so I can cross that out and cross that out. So really all I'm left with is 9 times, that's an 8, times 7, and that is actually equal to 504. Now you can use your calculator for this too. There's a nice little factorial button in there that'll solve it for you, but if you have to do it by hand, this is a nice little trick. So now let's talk about something called the recursive formula. So recursive might be a word you've heard before, maybe not. So let's start with talking about what recursion is. That's the process of choosing a starting term. So you define what the first term is, so a base 1 is whatever number, and you repeatedly apply the same process to the term before it. So the terms that come before whatever it is that you're looking for are really important in a recursive formula. So it's not just like, oh, I can find the 15th term, it's that I need to know the 14th, 13th, 12th, etc. term, which is slightly more annoying, but these kinds of patterns happen. Something to know, or two things to know actually, is that a recursive formula always has two parts. It has a starting value, so sometimes you're given 1 to 2 numbers that it starts with, and then also you're given an equation to find the rest of the terms to apply to that first or second, or however many terms you're given. Taking a look at this example, let's find the next 3 terms of this recursive sequence. So if I'm given the first 2 terms here, actually it starts with 1 and then 1. This is how you find the next 2 terms. So how I would start this is, now I want s of 3. So that means that I add the first 2 terms that come before it. So if n was 3, right, 3, right there, 3 minus 2 is the first term, and then 3 minus 1 is the second term. So another way to think about it is s base 1 plus s base 2, and I know those two things to be 1 plus 1, that's 2. So if I repeat the process and I want to find the 4th number in the series, or the sequence, sorry, I want s2 plus s3, so the 2 that come immediately before it. So s2 is 1 and s3 is 2. See why that one's important? Because without this, I couldn't find that. That's really what a recursive sequence is. So that's 3. And finally, let's find the 5th one. That's going to give me s base 3, s base 4, and 3 is 2, 4 is 3, and that's going to give me 5. So the next 3 terms are 2, 3, and 5. So let's lastly talk about something called summation. And it has the word sum already in the title, which means to add. So remember, a sequence where I add up all the terms is called a series. So we're talking about the summation of a series. That can be nicely explained with this capital sigma here, which means summation, or to add, in the Greek alphabet. And there are some parts to it. So there's always this thing at the bottom. So it could be a k, it could be an n, whatever. It's going to equal something. And that means your term that you start with. So it's also called the index. And then there's this number on top which tells you when to stop. So here we're going to go from 1 to 5. And this part right here is the formula to which you will carry out the summation. So if it starts with 1, it goes to 5, and you'll add each piece, 1, 2, 3, 4, 5, up. So let's take a look at this example. So if I start at 1, end at 5, for the function 5k, I'm going to do 5 times 1, 5 times 2, 3, 4, 5, etc., and add that all together. So the answer to that summation is actually one nice number, which is 75. Let's finish with 2 examples. So the first one is writing out the sum. Now the difference between the last example and this one is that I am working with an n, which is not a number, so I have to write my summation a little bit differently. So I know that my first term is going to be 1 factorial, the next one is going to be 2 factorial, 3 factorial, and it's going to end with n factorial. So I like to express at least 3 terms here. You had a plus, dot, 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 plus, and then your n, wherever that is inserted into your function here. Obviously you can simplify this, but I'm going to leave it that way for now. So my second problem here is to express using summation notation. And that means that I'm going to have my sigma, and I'm going to have something down here, something up here, and something right here. Now I left it in pretty obvious terms, but let's figure this out. So I start with 1, so I know my k is going to be 1, and I actually end with 9, which is different than ending with n, so it's going to be finite. So I'm going to put my 9 up here, and then I have to pay attention to the rule that's happening in each of these pieces. So it looks like whatever I input is going to be squared. So that means that I keep the same letter k here, and that is how I write that in summation notation.
And that's going to do it for this video. Thanks for watching.